The main part of this lesson is, well, an introduction to the number system. We're not necessarily going to do a history lesson, but we are going to learn how you could discover new numbers, even though this may not necessarily be how they were discovered. And then after that, we're going to hit a few other topics that kind of maybe stand alone, but everything's useful here. So we start with the natural numbers, and the natural numbers, also known as the counting numbers. This is just 1, 2, 3, 4, 5, and so on, right? 6, 7, 8, 9, 10. Those are the natural or counting numbers, and we're going to evaluate these and then answer the following questions. 2 plus 3, what is 2 plus 3, right? 2 plus 3 is 5. What is 7 plus 13? 7 plus 13, that is 20. All right, there's a point here. 22 plus 11, that is 33. And then 9 plus 4, that is going to be 13, right? Okay, so why are we doing this? Why are we doing addition here? It says right here, are the natural numbers closed under addition? What does this mean, right? In other words, is the sum of two natural numbers always a natural number? That is, if I take two natural numbers and I add them, will I get another natural number? Well, let's see here. 5 is a natural number. 20 is a natural number. 33 is a natural number, and 13 is a natural number, right? So, in other words, you're kind of stuck. That's why they say you're closed or you're trapped, right? As long as you add two natural numbers, you're only never going to get another natural number. There's no escape. But let's turn our attention to subtraction and see what happens. So, if I take two natural numbers, let's say 14 and 8, and I subtract them, let's see, 14 minus 8, that is 6. Okay, 6 is a natural number. Well, what about 8 minus 5? 8 minus 5, that's 3. 3 is a natural number. What about 7 minus 7? Well, 7 minus 7 is 0, and 0 is not a natural number. So we should kind of pause here and be like, whoa, what is that, right? We've never seen one of those before. We've never seen a 0 before. And historically, this is actually a pretty profound concept, the concept of 0. But anyways, then we have 4 minus 9, and that is negative 5. And again, this should kind of get our attention because we're like, whoa, what is that, right? What is negative 5? We've never heard of such a number before because the only numbers we know of are 1, 2, 3, 4, 5, right? The natural numbers. So what we see here is, we didn't answer this question. Are the natural numbers closed under addition? Yes, they are, right? Are the natural numbers closed under subtraction? No. Right, we just realized that if we subtract two natural numbers, we're not always guaranteed another natural number. We may get this, whatever that is, and we may get one of these numbers, right? Whatever types of numbers those are. So this broadens the system, right? There obviously must be more than just these numbers, right? There has to be something else. There has to be something beyond. That brings us to the whole numbers, and the only number that is considered whole, that is not considered natural, is 0. So there's nothing super crazy here. We're just going to tag on a 0 to our list and call those the whole numbers. Cool. All right. On to the integers, right? We are expanding our number system. We are expanding our knowledge of what numbers exist, right? The integers. Well, that's where we subtracted. Remember, we did 4 minus 9, and that gave us negative 5, right? So the integers here, we're just going to introduce the negative numbers to our whole numbers. And this gives us what are called the integers. All right, good. And so maybe thinking, okay, maybe this is it. Maybe we have positive numbers, we have 0, and we have negative numbers. And that's the number system, right? That's the entire number system. Well, let's keep going. We've added, we subtracted. You could probably guess what we're going to do next, right? The next thing to do would be to multiply integers and see what happens. So if I multiply 5 and 6, which are both integers, I get 30, which is another integer. So far we haven't discovered anything new yet. Let's go negative 7 times 2. Both of those are integers. If I multiply that, I get negative 14. Negative 14 is also an integer, so nothing going on here. And then if I multiply 4 and negative 3, I get negative 12. Negative 8, negative 11 is positive 88. But we haven't broken out of or escaped from the integers. If we multiply two integers, any mixture of positive and negative, we're going to get another integer. Okay, well, what comes after multiplication, right? Oh, let's answer this question first. Are the integers closed under multiplication? No. Yes. Right? If we multiply two integers, we are going to get another integer, right? That's what it means to be closed. Now for division. All right, let's divide two integers and see what happens. Well, 18 divided by 6, that is 3. That's an integer. Negative 36 divided by 9, that's negative 4. Well, negative 4 is also an integer. So far, we're stuck in integers. Okay, what about 3 divided by 2? Is there a number in this list that would satisfy 3 divided by 2? The answer is no, there is not. There is no integer that would satisfy 3 divided by 2, right? 3 divided by 2 is, well, that's 3 halves, or 1.5, but let's leave it at 3 halves. So again, it's like, wait a minute, what is that? Right? That's a number we've never seen before, right? We're discovering new types of numbers. Let's see what else we can discover. What about 10 divided by 3? Well, 10 divided by 3, also a fraction, if you will. You could convert that to a decimal. But point being here is if we multiply integers, we're only ever going to get integers. That's what it means to be closed. But if we divide integers, we're not always guaranteed to get another integer. Sometimes we will, but sometimes we won't. So, are the integers closed under division? No, they are not, right? We are on the frontier of a new type of number, and that number is called the rational number, right? So we are expanding our number system. We are discovering new numbers by applying operations and seeing where that leads us. So the rational number here, a rational number is any number that can be expressed as p divided by q, where p and q are integers and q does not equal 0, right? You cannot divide by 0. Look, that's a lot. Just think of it this way. A rational number is a number that can be expressed as a fraction, right? That's the more informal definition. Decimals. In decimal form, the decimal form of a rational number either terminates or repeats, right? If it's rational, the decimal has to terminate or repeat. And then note that the rational numbers include all the natural and the whole numbers and the integers, right? We're just making our circle bigger as we move along, as we discover new numbers. So a few examples of rational numbers, what will be like what we had before, right? Over here, these are examples of rational numbers, or specifically non-integer rational numbers, right? Because integers are rational as well, right? So we have these fractions here, 3 halves, which, is 1.5. That is a terminating decimal, so it's rational. 10 over 3. Well, that would be 3 point repeating 3, and that's okay, right? We said that repeating decimals are rational. That's fine. What else would be rational? I mean, anything you could think of, any fraction you could think of, right? Where both the top, the numerator, and the denominator are, integers, right? Negative 7 over 5 would be a rational number. And don't forget that a natural number like 2 is technically rational, right? How do you know that 2 is rational? How do you express 2 as a fraction? Well, you could just put it over 1, 2 over 1, and there you go. You've expressed 2 as a fraction, which satisfies the definition of a rational number. Okay. Well, we've added, we've subtracted, we've multiplied, and we've divided, and the subtraction and the division led us into new territories, into new numbers, discovering new numbers. So what other type of operations could we apply here and see where that leads us? Because we're not done. The rational numbers is not all there is. All right, well, let's see here. Evaluate the following, and then we'll answer below. So 7 squared, well, that means 7 times 7. That's 49. So have we broken free of the rational bubble? Well, no. 49 is still a rational number. How about negative 8 squared? Now, this means negative 8 times negative 8, and a negative times a negative is a positive, right? So that's 64 right there. Have we broken out of the rational bubble? No, we have not. 64 is irrational. 2 fifths squared, that would be 2 squared over 5 squared, which is 4 over 25. Now, is 4 over 25, is that not a rational number? No, it is rational, right? It's a fraction, so we haven't broken out. And then 1.1 squared, that's going to be 1.21, right? I think 11 squared is 121, so 1.1 squared will be 1.21. 0.21. Now, is this a rational number? Well, let's see. It's in decimal form and it terminates. So yes, it's rational. Squaring rational numbers does not get us out of the rational numbers, right? See, are the rational numbers closed under the square, the second power? And the answer is yes. If you square a rational number, you're going to get a rational number, okay? So let's try something else. Let's see if we can break out of the rational bubble. Here, let's do the square root. The square root of 16 is 4. 4 is a rational number, all right? How about the square root of 81? Square root of 81 is 9, all right? 9's rational, so we're not getting anywhere yet. How about the square root of 100 over 9? Well, that's just the square root of 100 over the square root of 9, which is 10 over 3. 10 thirds. Is that rational? Yes, right? That's a fraction. It's rational. Okay. How about the square root of 5? The square root of 5. Can we do to 5 like we've been doing to all these other numbers, right? We had a 16, we had an 81, we had 109. Can we do that with a 5? Can we do that with a 5? And the answer is no, you cannot. In fact, I should have brought my calculator. Let me grab my calculator real quick. And you can still hear me talking. If I type in the square root of 5 into my calculator, I'm going to get this number. I'm going to get 2.236067977. And the only reason why that stops is because the calculator runs out of room. That's not because that decimal terminates. In fact, this decimal does not terminate. It goes on forever with no pattern, right? No obvious pattern, at least. I'm not sure. I'm assuming there's no pattern. I don't think there is, right? But the point being here is that this decimal does not terminate. And that disobeys the definition of a rational number, right? A rational number in decimal form needs to terminate. This doesn't. Thus, we have broken out of the rational bubble. How did we do that? We took the square root of a number that is a non-perfect square, right? 16, 81, 109, those are considered perfect square numbers. 5 is not. And if we take the square root of that, we are going to get a non-terminating decimal, which means this number is not rational. So yet again, we have discovered a new type of number that we've never seen before, right? Are the rational numbers closed under the square root? No. No, it is possible to take the square root of a rational number and get a number that is not rational. So what are we going to call those numbers? We're going to call them irrational numbers, right? Big surprise there. We're going to call them irrational. So here we go. It's just the opposite of rational. An irrational number is any number that cannot be expressed as p over q, where p and q are integers and q is not 0, right? The decimal form of an irrational number is non-terminating and non-repeating. It doesn't end, and there's no pattern involved, no repeating pattern involved. All right, so what are some irrational numbers? Well, basically, like this, right, we have the square root of 5. Just pick a non-perfect square number, like 11, and take the square root of it, and boom, you have an irrational number. Those right there are irrational numbers, right? How about the square root of 16? Well, the square root of 16 is 4. That's rational, right? So that doesn't count. That doesn't work. That's a rational number. You have to pick a number that you can't square root evenly. That would be, instead of 16, you could do 17. The square root of 17, that would be irrational. Now, there's a very famous irrational number that's of a different type than these. I'll give you a minute to think about it. Think circles. Think, what famous irrational number is associated with circles? And that would be pi, right? Pi. And pi is about 3.14159, right? But it doesn't end there. It actually goes on forever. Pi in decimal form doesn't terminate. It never ends. And that's part of the definition of irrational. Another famous one, kind of like pi, is Euler's number. This has, it's its own number too, but 2.718, I believe, but it goes on forever, right? These are irrational numbers that the decimal forms never end. The decimal forms never end. So these are some examples of irrational numbers. Okay, cool. So thus far, we started with natural numbers, and we, from there, discovered the whole numbers, discovered the integers, and then we discovered the rationals, and then we discovered the irrationals. So you may be thinking, well, surely this completes the number system. This has to be all the numbers that exist. We have finished the discovery, right? We have seen everything that there is to be seen. No, we have not. But this does bring us to a checkpoint, if you will, a pretty significant step in the journey, is that the rational numbers and the irrationals combined make up what are called the real numbers. So all the real numbers is everything that we've discovered so far all together. We're going to name them the real numbers. So any number that is rational or irrational is real. This includes all the numbers thus far mentioned. So anything you can think of that we've done so far is in the big category of real numbers. So that could be 5, that could be the square root of 5, that could be 5 divided by 2, it could be -5, right? It could be the square root of a perfect square like 36, which is really just 6, right? That's rational. Which means it's real. You could have pi, you could have the square root of pi. You could have pi, right? A lot of pi examples. Pi divided by -3. That would be irrational, but bigger, it's real. These are your real numbers. So we're just going to keep doing what we've been doing. Apply operations to real numbers and see if we can break out. Can we get out of the universe of real numbers? Well, let's see here. Evaluate the following. Square root of 36, that's 6. Okay? 6 is a real number. All right, we have not broken out of the real numbers. How about the square root of 144? That's 12. Right? 12 is rational, but right now we care about that it's real. That's what we care about. It's a real number. It's a real number. How about the square root of 7? Well, I'm gonna cheat here. Use a calculator here. Square root of 7. Square root of 7. So the calculator gives me 2.64575. 1311, right? And the calculator stops because that's as far as it can go, but this number does go on forever. This decimal goes on forever. So this is not rational. This is an irrational number, but it's still real, right? We haven't broken out of the real numbers. And that brings us to the square root of -25. Now, I get it. The temptation here is to say, well, that's -5. Well, we'll pause real quick. Pause. -5 squared is -5 times -5. That's a negative times a negative, which is positive 25. So if -5 squared is positive 25, then the square root of -25 can't be -5, right? In fact, this is 5i. This is a new number. We just discovered yet a new type of number that we haven't seen yet. This is not natural. This is not whole. This is not an integer, and it's not real, right? So we give the name imaginary. The name's a little bit misleading, but I'll save that topic for a different time. We call it imaginary numbers. That's just the name we've given it. So are the real numbers closed under the square root? No. If you square root a negative number, you're going to break out of the real numbers into the realm of imaginary numbers, a whole new type of number that we have never seen before in this video, of course. But all right, so the imaginary numbers. An imaginary number is any number that can be expressed as bi, where b is a real number and I is equal to the square root of -1. Let me go back here real quick, because I didn't address that it is the square root of -1. This right here, this -25, could be broken apart into a 25 and a -1, right? And then I could split up this square root into root 25 times root -1. The square root of 25 is 5, and the square root of -1 is I, right? So that's where that comes from. I is just what we're going to call the square root of -1. We got to call it something because we don't have anything yet that equals that, right? So we call it I. We call it I. It's the square root. Whatever the square root of -1 is, we're just going to call it I, all right? All right, so what are some imaginary numbers? You just pick a real number, 8, and put an I after it. Boom, there you go. You got an imaginary number, 8i. Cool. You could also have -8i. Make it negative, right? What else? You could do a fraction, 7/9 I. That would be an imaginary number. As long as the number in front of it is real, tag on an I, it becomes imaginary. You could have the square root of 5 with an I at the end, right? That's an imaginary number. So, good. Realize that some of these things are nested or embedded. For example, all natural numbers are whole numbers, and all whole numbers are integers, and all integers are rational, and all rational are real. But rational and irrational are mutually exclusive, right? It's like, okay, a dog is a chihuahua is a dog, right? All chihuahuas are dogs, but then you have this whole other class of cats, right? They're mutually exclusive, and that's the rational versus irrational, and that's also real versus imaginary, right? These are two completely separate realms. They're mutually exclusive. They don't have anything in common. When we put these two things together, the reals and the imaginaries, we get what's called a complex number. And complex numbers come in the form a plus b I, where a and b are real numbers and I equals the square root of -1. The complex numbers include every number thus far mentioned, and finally, this completes our number system, right? So there is... I believe there's unanimous agreement amongst the world of math that this is it. This is the whole number system, right? If you add two complex numbers, you'll get a complex number. If you square root a complex number, you'll get a complex number. There's no operation that will allow you to escape from the realm of complex numbers. This is it. This is the end. It only took us several thousand years as a human race to get here, but hey, be thankful we're living at the end of it, right? We've discovered a lot. But anyways, so this could be something like 2 plus 3i. This could be something like 5 minus I. That's a complex number. It could be something like the square root of 2 plus the square root of 3i, all divided by 4. That's a chunky complex number, but it's a complex number all the same. We could throw in some pi, right? We could do pi plus 2 pi I, right? Why not? Get creative with it. We could have a -5 pi plus the square root of, the square root of pi I, right? These are a little crazy here, but they're complex numbers all the same. So anyways, the point being here, well, what is the point? What is the point? It's called the test for closure, right? So you add two numbers, add two natural numbers, you'll get another natural number. But if you subtract two natural numbers, you may not always get a natural number. So it's not closed under subtraction. And this type of testing leads you to new types of numbers until you arrive at the full picture, which is the complex numbers. So that is our number system. And that's how you can kind of develop it. So, all right, cool. Let's move on to just some other topics. Now, they're still related, but let's talk about the perfect square numbers. We've mentioned these. These have been brought up. List the first 15 perfect square numbers beginning with 0. So what do I mean by this? I mean, okay, I want 0 squared. I want 1 squared. 2 squared, 3 squared, 4 squared, and I want that all the way up to 15 squared. Now, if you're feeling ambitious here, pause the video and write those out. I'm going to write them out right now. That's going to be 0, 1, 4, 9, 16, 25. Okay, 6 squared is 36, 7 is 49, 8 squared is 64. 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared, a lot of people memorize up to 12. Let's get 13, 14, and 15, not that hard. 13 squared is 169, and then to get 14 squared, all you have to do is flip the 9 and the 6 for a 196. So 13 squared is 169, 14 squared is 196, and 15 squared is 225, which is, I don't know, that's a nice number. So these shouldn't be too hard for you to add to what you already know. But good. All right. To all my classes that I have, I strongly recommend memorizing these numbers. I mean, My goodness, how much easier your life will be in a college algebra class, for example, if you had these numbers memorized. At least be able to recognize them, right? Because what we're going to do next, we're going to simplify square roots next. We're going to simplify square roots. And you've probably been taught to do this with a factor tree. And that's fine. There's nothing wrong with that. I'm going to do it differently. But the way I do it requires that you are very familiar with the perfect square numbers if you don't have them memorized. Here's how I do it, right? So I say simplify the following square roots. Use a factor tree. I'm not going to do that. Those are old instructions. Or pull out a perfect square number, right? This is the way I like to do it, but you have to be a little smooth with your square numbers. But here we go. Square root of 121. Well, that's 11, right? That one's clean. Done. Square root of negative 81 is, well, square root of 81 is 9, and then the negative just tags along. So that's negative 9 right there. How about the square root of negative 36? Well, again, this is, I'll break this apart. Negative 36 is technically 36 times negative 1. And then we can split this up. Square root of 36 times the square root of negative 1, right? And the square root of 36 is 6, and the square root of negative 1, right? That's your imaginary number, I. So the answer here is 6i. And then we get on to the square root of negative 144, right? You do the same work we did here, but this time it's going to be a 12i. So, okay, those are straightforward. Really, those all involve perfect square numbers, so that's nice. That's easy. But what about something like 75? I have 75 here twice because I was going to do once with a factor tree and then once the other way. But you can find another video on YouTube if you need to do the factor tree. So I'm just going to do it once. Okay, here's what I mean by pull out perfect square numbers. I'm looking at 75, and I'm like, okay, 75. 75. Is 75 a perfect square number? Is it on this list? No, it's not. Okay, so it's not going to be as clean as the first 4 examples here. So how do we handle this? Well, 75 may not be on this list, but it is divisible by something on this list. So I want you to take a minute here and think. 75 is divisible by which of these numbers? 25. 75 is divisible by 25. We're going to use that, make our lives a little bit easier here. So 75 is 25 times 3. And that's how you're going to split it up. Break it apart. Square root of 25 is 5, and then root 3 is just root 3. And you're going to leave your answer like that. That's how you simplify the square root of a non-perfect square. Pull out a perfect square number, but you have to know what your perfect square numbers are, right? Okay, good. Let's do this with, here we go. We got a negative 72. So 72, is 72 on your list of perfect square numbers, right? If we go up here and we look at this list, is 72 on this list? No, it is not. Right? But is it divisible by something on this list? So you're more than welcome to pause the video and try to figure it out by yourself, but I'm going to say it right now. 72 is divisible by 36, right? It is 36 divided by 2. Sorry, it is 36 times 2. So we're going to break apart the 72 into a 36 and a 2. And then separate the square roots. And the negative is just going along for the ride, right? Anyways, you get the point. All right, so square root of 36 is 6, and then root 2. All right, there you go. That would be the answer there. Same train of thought. Is 45 a perfect square number? No, it is not. However, it is divisible by a perfect square number. Which perfect square number is 45 divisible by? 9. We're going to break this apart into a 9. 45 is 9 times 5. And then I'm also going to peel off the negative and do a negative 1. We can separate. We have 3 pieces now. We have the square root of 9. We have, I'm going to put the I in the middle here. It's just standard practice. You can rearrange these. All right, square root of 9 is 3. Square root of negative 1 is I. And then root 5 cannot be simplified. So you would leave it like this, 3I root 5. And that's how you simplify a square root, a radical. All right. Pause the video. Try one of these. See what you can figure out. I'm going to speed through them very quickly. 28. You could break that apart into 4 times 7. The square root of 4 is 2. You cannot simplify root 7. 12. Again, you want to be strategic. You could break apart 12 into 6 times 2, right? Let's do that. But neither 6 nor 2 are perfect square numbers, so this doesn't get you anywhere, right? This doesn't help you. You want to break it apart into useful numbers. So here, that would be 4 and 3. Why? 4 is a perfect square number, and the square root of 4 is 2, right? So this is negative 2 root 3. 18 can be broken apart into 9 and 2. Why do we like that? We don't want 6 and 3. 6 times 3 is 18, but 6 and 3 aren't perfect square numbers. 9 is a perfect square number. That's the one you want to use. And then peel off the negative 1 for a 3I root 2. The 3 comes from the 9. The I comes from the negative 1, and the 2 doesn't leave the roots because you cannot simplify root 2. 125 is not a perfect square number, but 25 is. 125 is 25 times 5. That's what you want to break it up. Square root of 25 is 5. The other 5 stays. And that is simplified. Right here, if you have a calculator on you, I want you to type the square root of 125 into your calculator. And then after that, I want you to type in 5 root 5 into your calculator. And assuming you did so correctly, you will get the same number, right? That's what it means that these are equal. One's just simplified. So they are, in fact, the same quantity. The value of root 125 is the same as the value of 5 root 5, right? Okay, 169. 169, that's a perfect square number, right? What's the square root of 169? Well, it's 13. And because it's negative under the square root, it's 13i. There you go. I was just making sure you memorize these bigger square roots, right? Memorize the square roots. It's good for you. All right, 48. 48. Now, careful here. 48 is divisible by 4, which is a perfect square number, right? That would be 4 times 12. Now, that would give you 2 root 12. Okay, yes, but let me add here something. You don't want to just pull out a perfect square root. You want to pull out the largest possible perfect square root. And whereas 48 is divisible by 4, it's also divisible by 16. So most simplified is 4 root 3. But speaking of typing these things into your calculator, if you type root 48 into your calculator, and you type 2 root 12 into your calculator, and you type 4 root 3 into your calculator, you're going to get the same thing for all 3 of them, right? All 3 of those have the same value. They're just in different forms. One simplified more than others. All right, negative root 50. Whoa, come back to me right here. Here we go. All right. 50 is 25 times 2. And so you end up with negative 5 root 2. 640. My goodness. Oh, 64. Right? There you go. Don't overthink that. That would be 64 times 10. So 8 root 10. Okay. And that right there is how you simplify square roots. Again, you may have been taught to use a factor tree, which is totally fine. If you like that, you do it. You do it how you want it. But here is a more efficient way to do it. But this does require that you have significant familiarity with the perfect square numbers, right? So there you go. What's next? Next, we're going to talk about the absolute value, because why not, right? We're just sticking in everything here. So the absolute value measures the distance a number is away from zero. It cares about distance, not direction, right? It doesn't care if it's left or right. It's just how far away from zero is it. Informally, the absolute value makes the number positive. The formal definition is below. This is the formal definition of the absolute value function. You can ponder that if you want, but we won't overthink this. So here we go. We're going to simplify these. 2 times, all right, 8 minus 15. 8 minus 15 is negative 7. The absolute value of negative 7 is positive 7. So when you satisfy the absolute value, when you take the absolute value, you can switch to parentheses. That signals, hey, I have taken the absolute value of negative 7. It is positive 7, and we can multiply for a final answer of 14. Also, side note, think of PEMDAS, right? Think of PEMDAS, which P, you're supposed to do parentheses first. The absolute values, in addition to making everything positive, function as parentheses. They are to be treated as parentheses in addition to their definition. So that means you could almost think of there being parentheses here, which means we need to do the 13 minus 8 first. 13 minus 8 is 5 minus the absolute value of negative 6. I'm going to do both absolute values in one step. The absolute value of 5 is 5, and the absolute value of negative 6 is positive 6. And 5 minus 6, what's 5 minus 6? 5 minus 6 is negative 1. The answer to that problem is negative 1. This one looks fun. We have actual parentheses in this one that we have to do first. So we have 16 minus 4, parentheses here, 5 minus 2 is 3, plus 3 absolute value. Okay, so we have subtraction, multiplication, and addition. According to PEMDAS, the next thing to do is multiply. That's going to be 12 plus 3. Now, when you need to add and subtract, you're just going to work from left to right, even if that means subtracting before adding. But that's another lesson. 16 minus 12 is 4. 4 plus 3 is 7, and the absolute value of 7 is 7. So the absolute values didn't really change anything there. It ended up being positive 7. Anyways, all right, so that's that one right there. 12, 64 plus 3. Yep, that looks good. Okay, so here you go. Pause the video if you want and try some of these. Give these a shot. I'm going to do them right now. The absolute value of negative 17 is 17. Congratulations. 5 minus 14 is that negative 9? I hope so. And the absolute value of negative 9 is positive 9. Eight minus 11 is negative 3 plus 3. The absolute value of negative 2 is positive 2. So I'm going to switch this negative 2 right here. I'm switching that to a positive 2 and switch it to parentheses. The absolute value of negative 3 is 3. 3 times 2 is 6. 3 plus 6 is 9. 10 times 9 is 1. 10 minus 11 is negative 1. Ooh, okay. Those are absolute values and those are ones, right? So the absolute value of 1 is 1, and the absolute value of negative 1 is 1, and 1 minus 1 is 0. Answer there is 0. All right, pay attention, right? Parentheses first. This is kind of an inside. You work your way out with these types of problems. So we'll deal with the 9 later. 7 minus 5. Here we go. 4 minus 2. We got to do that first. 4 minus 2 is 2 plus 5 absolute value. And then inside the absolute value here, well, no, I'm getting ahead of myself. We need to multiply next. According to PEMDAS, we need to do 5 times 2, which is negative 10, plus 5. Good. Now, within the absolute values, we're going to work from left to right. So this is 9 minus, I'm going to do this in one step, 7 minus 10, that is negative 3. 7 minus 10 is negative 3, plus 5 is positive 2. The absolute value of 2 is 2, 9 minus 2 is 7. Minus 2 is 7. What's the difference here? Yeah, I see the difference. Okay, good. Let's start with that subtraction first. 7 minus 3 is 4. Next, on to multiplication. 2 times 4 is 8. 1 minus 8 is negative 7. The absolute value of negative 7 is positive 7. Multiplied by 3 is 21. The answer there is 21. Okay, there you go. Those are the solutions. Okay, adding negatives. Adding negatives. Let's talk about this. Yet another topic useful to you in an algebra class. Adding a negative number is the same thing as subtraction. So 7 plus negative 2, that's the same thing as 7 minus 2, which is 5. Negative 11 plus negative 5 is the same thing as negative 11 minus 5. Okay, pause. This trips people up, and understandably, put money to it, right? If you spend $11 minus 11, and then you spend 5 more minus 5, how much money have you spent, right? And you have spent $16, negative 16. You are down $16. All right. What about negative 6 plus 15? This is the same thing, if it helps you. This is the same thing as 15 minus 6, which is 9. And here we go, we have negative 15 minus negative 6. Whenever I subtract a negative, right, a double negative makes a positive. And then in the previous problem, I told you that this is the same thing as 6 minus 15. But just be careful here. 6 minus 15 or negative 15 plus 6, however you want to think about it. You have $6, but then you spend 15. You are now in debt, right? How much are you in debt by? $9. This is negative 9. So, good. All right, pause and try these 4 problems. I will answer them quickly right now. This is the same thing as 19 minus 8, which is 8. This is the same as negative 8 minus 3, which is negative 11. This is the same. No, I'm just going to do it. Negative 12 plus 5, negative 12 plus 5. It's like you were in debt $12 and you paid off $5. You're still in debt, but a little bit less. You now only owe $7. Negative 6 minus negative 10 is the same thing as negative 6 plus 10, which is 4. All right. And that brings us to what I called extra practice. Simplify the following expressions. So here's some other problems you may face in your class. Root 32 minus root 50. We're going to simplify those the same way we simplified them before. 32 is not a perfect square number, but it is divisible by 1, and that is going to be 16. 32 is the same thing as 16 times 2. 50 is the same thing as 25 times 2. Simplify, this becomes 4 root 2 minus 5 root 2. All right, why? The square root of 16 is 4. The square root of 25 is 5. And the 2's stay underneath the square root. All right. Now, this is like combining like terms. If I asked you, for instance, what if I asked you what 4x minus 5x was, right? That would be 4 minus 5. That would be negative 1x, or just negative x. This problem is like that, but instead of an x, you have a root 2. So 4 root 2 minus 5 root 2 is negative 1 root 2, or you could just say negative root 2. That is the answer. Okay, same thing over here. Okay, negative 12. We want to break that apart into negative 4 times 3. And 75, we want to break that apart into negative 25 times 3. This is how you know the problem is going somewhere, because you have these matching numbers. See how both of these produce a 3? That's good, right? That means this problem can be simplified. What's the square root of negative 4, right? The square root of negative 4 is going to be 2i, and then root 3 plus the square root of negative 25 is 5i, and then we leave behind the root 3. Now this is good because they both have root 3s. You need this. In a sense, you are combining like terms. 2i plus 5i is 7i, and then you tag on the root 3. 7i root 3 is the answer there. What do we got going on here? I'm just combining everything, the square roots and the absolute value. So the square root of 81 is 9. The square root of 144 is 12. Negative 9 minus 12, right? That's you spend $9, you spend 12 more, and then you have spent 21. The absolute value of negative 21 is positive 21. That is the answer there. All right, last 3 here. Negative 8 plus. What is 5 minus 9? 5 minus 9 is negative 4. Negative 8 plus negative 4 is the same thing as negative 8 minus 4, which is negative 12. Okay, these are the same exact problem, except the one has absolute values, and we're going to see how that changes the problem, because it will change the problem. Actually, let's leave these side by side. This is negative 8 plus the absolute value of negative 4. Well, the absolute value of negative 4 is positive 4, right? So instead of negative 8 minus 4, we now have negative 8 plus 4. That's what the absolute value changed. Negative 8 plus 4 is negative 4. Here's just another simplify the square root of negative 450. Okay, 450, that's divisible by which perfect square number? Pause the video, try to think about it. 450, it's divisible by 25. Can you go bigger, though? The answer is yes. It's 225 times 2. And 225, what was the square root of 225? That was 15. Because it's negative, it's going to be 15i root 2. That's the final answer. Hope this helped. There's the last 6 problems if you want a full view of that. All right, we'll see you in the next one.